Today's lesson is going to be over working with matrices in MATLAB and solving systems of equations. And for this, it's just going to be really all built-in stuff, so this isn't going to be too challenging. Let's start off with a matrix. I'm going to leave some comments up there because we'll talk about maybe its size. Let's say A is equal to, and how about 2 minus 3, 1. Okay. And remember, when you do this, if you want to switch to the next row, you want to use a semicolon, and you could keep going all in one line. Okay, so you could say that our next row here is minus 6, 2, and 9. Okay, but if you would prefer, so that it's easier to look at this 2 by 3 matrix, okay, and that just meaning 2 rows, 3 columns, that's all that means. Alright, if you want it to be easier to look at though, you can just hit enter here, and MATLAB will understand that both of those things mean the same thing. Okay? And by both of these things I mean whether I type it in like this, and in fact you can see if I move up my command window here, you can see it made 2 minus 3, 1 the top row, and minus 6, 2, 9 the bottom row. But it'll do the same thing even if I put this space here, which is nice because you can kind of line things up if you choose to. Let's see. That looks good enough. Okay. And I'll go ahead and run it again, and you can see we're getting the same thing. Okay. The next thing I want to talk about here are vector and matrix operations. So of course we can do things like we can add to matrices as long as they have the same dimensions. We can multiply them as long as their inner dimensions match. We can do scalar multiplication, but also we can do some other types of operations which we've actually already seen in this class, but I think it might be helpful to see an explicit example where we have the matrix A right in front of us. So if you wanted to do a number divided by a matrix, this actually doesn't make any sense. And if I hit run, oh, and I already have the error down here so you can actually see it. You can see that it's saying matrix dimensions don't agree, and it's just not an operation, a number divided by a matrix. But let's say that I did actually have reason to maybe do 10 divided by 2, 10 divided by minus 3, 10 divided by 1, 10 divided by minus 6, 10 divided by 2, and 10 divided by 9. Right? There might be an application where I want to do that. And so here is the fix. You just put the dot here to perform such an operation. Right? And you can see it's done that. 10 divided by 2 is 5. 10 divided by minus 3 is about minus 3.333, and 10 divided by 10 is 10, and so on. And I was just going along the top row there. Let's go ahead and put a matrix B in here, and maybe we'll do, actually maybe 2 more matrices. How about B and C? So let's make B a, how about another 2 by 3? Let's do that. So there's our second matrix, and why don't we suppress both of these? Okay. And let's add one more. I'm comment this up here though. A and B are 2 by 3 matrices. And let's see, let's make this one a 3 by 3. 3 by 3. I'm just choosing random numbers here. Okay, so now that we have this, you all have noticed many times the error messages that MATLAB will get you if you're working with vectors or matrices, and the dimensions don't match. But I want to talk about it a little more. For instance, the matrix A and B, since they have the same dimensions, we can actually add those together. But A and C will result in an error message. And let's go ahead and just test both these out. Okay. So I'm just going to write matrix operations. Okay. So A plus B, we expect no issues. Okay. And you can see here we have 11 minus 3 plus minus 4 is minus 7. 1 plus 3 is 4. Everything looks fine. Well, let's say we try and do A plus C. Okay, and we have matrix dimensions must agree, right? Matrix addition requires the same dimensions. All right, let's see what else. Let's maybe do matrix multiplication. Okay, and I'll probably change what I've written there a little bit. Let's try and do A times B. Okay, A times B. Okay, dimensions must agree. And so the way it works with matrix multiplication, to multiply two matrices, the matrix, or the first matrix, must have the same number of columns as the second matrix has rows. Okay. And so you can see A and B both have 3 columns, while C does have 3 rows, which means we could do A times C, but we couldn't do A times B, right? Let's try A times C this time. Oop. Oh, it's still giving us an error based on this A plus C. Maybe I should get rid of that. There we go. Okay. So it's performed the matrix multiplication A times C. And actually, if we were to go the other way, note that C has 3 columns, okay, has 3 columns, while A and B have 2 rows. So if we were to try and do maybe C times B or C times A, it doesn't really matter which one, we should end up with an error message. Let me just suppress this one. Okay, and there's our error message. Okay. Now, let's say, and this has to do with the dot again. Let's say that we wanted to not matrix multiply A and B, but to multiply all their elements. Okay, so multiply, 2 times the 9, minus 3 times the 4, 1 times the 3, minus 6 times the minus 2, and so on. That's where the dot would come into play. So if I were to do A times B, but with the dot, I would just need to note that we would like A and B to be the same dimensions because we're going to multiply the element in row 1, column 1 in each one of the matrices, and then we'll go over and we'll do the one that's in row 1, column 2, and multiply those from both matrices, and so on. Okay. And let's just check and see that this works as expected. And you can see 9 times 2 is 18, minus 3 times minus 4 is 12, okay, and so on. Okay. All right, and the next thing I want to talk about, we've also done a little bit of, and that is maybe pulling rows or pulling columns or just pulling an element from a matrix. Okay. So we're going to pull an element from row 2, column 1, or actually let's do column 3. Row 2, column 3 of matrix B. Okay. So if we wanted to do that, you just go B 2, comma 3. And if we look up here, that should be 0, 2, comma 3, row 2, column 3. Okay. And I'm going to suppress everything else. Okay, and you can see it's 0. Okay. Let's say we wanted to pull an entire row. Okay, let's go pull row 3 from matrix C. Okay. So you could imagine for C here, we would like to, again, take row 3. So we'd like the third row. And the way that we say all the elements from row 3 is just with a semicolon, or with a colon. Okay, let me suppress this and we'll run. And you can see we get the 0, 1, 4. Okay. All right, and of course, if we wanted to do a column, like let's say we wanted to do column 3, then we'd put 3 here and we'd put the colon here. All right. All right, and then I'd like to talk about some kind of special matrices. And we've actually seen some of these, but not all of them. One is we've seen the zeros function, okay, which allows you to, let's say you want to make a 5 by 6 matrix of zeros. Well, you can. Let's maybe call this Z. Okay. And I won't suppress that. And let's say you want to make one filled with ones. Okay, maybe I'll call that capital O. You can do pretty much the exact same command ones, and then you could say 5 by 6 if we wanted it to be the same size. And one other one that, and we'll use all three of these here and there, I. Okay, and this is the identity matrix that you all are aware of. Maybe I should say for Z here, matrix filled with zeros, and let's state its dimensions. Okay. And same here with the ones. And then this last one's going to be the identity matrix. And I suppose let's make this thing a 4 by 4. Okay. The identity matrix has to be square. So, you know, in these other ones, you had to type in the number of rows and columns. For the identity matrix, you just have to enter in one of the dimensions because, again, it will be square. And the command for this is I. Okay. So let's take a look at all three of these. Okay. And so you can see our 5 by 6 filled with zeros, our 5 by 6 filled with ones, and then our 4 by 4 identity matrix. And one more thing you can do is you can check the size of a matrix, its dimensions. Okay, let's see. Let's do this with the ones matrix. Okay. So if we're going to do that, we'll say M and N. Okay. The M will be our number of rows, N will be our number of columns, and then we'll put in here equals size, and in here we'll use the matrix O. Okay. And so we should get M is 5, N is 6. There we go. Now let's go ahead and switch over and start thinking about systems of equations. So we'll still be working with matrices. All right, so I have a problem here for us. And we actually did some parabolic interpolation, but we used MATLAB's built-in functions. And is what I'd like to show you is that we can do parabolic interpolation pretty easily without the built-in function polyfit that we used. So the idea is we have some or in our case parabola, ax squared plus bx plus c, and we'd like it to pass through these 3 points. Okay. So what we're going to do is we're going to plug in those x values and y values. So if we were to plug in, say, 1 in for x, okay, our equation would wind up looking like a times 1 squared, or times 1. I'm going to actually write in the 1 there. Okay. And this is all going to be in comments. We'd have a times 1 plus b times 1, okay, plus c. And right, there's nothing we can plug in there, but I'm going to write a 1 there just because we're going to turn this into a matrix, and I just want it to be clear that, hey, this first row, all the numbers in front, our coefficients are 1, 1, 1. Okay. And then equals the y value, and we want the y value to be 3. Okay, so this is our first equation. And now we're going to have another one. We're going to have a times, and this time we're going to square 3. We're on this point 3 comma 10. So that's going to be a 9. And then b times what? Well, b times 3. And then c, again, we're just going to have a single c because we don't have any x that we can plug in. And then the y value is 10. Okay. And then one more equation. Okay. If we went and we plugged in 5 comma 5, then we have a times 25, it's 5 squared, plus b times 5, and then plus c times 1, which is equal to 5. Okay. And so if we were to write this in matrix form, okay, we would have, and let's go ahead and call this, let's call this matrix A. Okay. So our first row should be 1, 1, and I'm going to put a little bit of space there. 1, 1, 1. Okay. And this is just the coefficients. In a separate matrix, we will put y here. We'll put in, maybe I'll just put y in here right now so you can see it. This 3, 10, 5, 3, 10, 5, and I'm just going to scoot this over. Okay, that looks a little better. Okay, and now for the rest of A, I'll scoot this down a little bit. For the rest of A, we should have 9, 3, 1. That's our second row. And then our third row, 25, 5, and 1. All right, there we go. And so this, I want to comment this in here. Okay, so we're going to say that this leaves us with the matrix equation, A times X is equal to Y. Okay, and I'm going to call this matrix X here, I'm going to call it coefs. Okay. So some matrix times the vector of coefficients A, B, C will give us this vector Y. Okay. And maybe I'll point out, again, these are our coefficients here, A, B, and C. And that's what we're trying to solve for. We're trying to solve for this. Okay. And now we're going to have two ways that we can do this. Okay. One is you could find the inverse of A. Okay. And so if we did that, then we would want to do, right, we'd want to left multiply by A inverse. So we'd end up performing the inverse of A times Y. Okay. So let's see what that's going to look like. That would look like, and I want you to just see that this actually gives us the inverse matrix real quick. So I have INV and then A. And I'm going to move that up a little bit. Okay, so there it is. So you could verify this by hand, right? You could do the matrix A, and then you could augment it with the matrix I. You could row reduce until the first three, until that first 3 by 3 turns into the identity, and whatever you have on the right is your inverse matrix. Okay, but we can check this another way. There's a little bit more simple way to check this. We could just do A times A inverse, and this better give us the identity. Okay, and it does. You can see that there are some actual, clearly since this is minus 0.0000, somewhere out here is a non-zero digit if we were to keep going. Okay, so there is a little bit of error there. Okay. All right, next, let's actually solve this system. Okay, so to solve this system, we are going to do exactly what we said. We're going to take the inverse of A, and we're going to multiply it by the matrix Y. And this should leave us with our coefficient matrix. Okay, and I should say coefficient vector. A vector that contains little a, little b, little c that go on that parabola. Okay, okay, and there they are. And now the question is well, how do we tell that this is the right answer? How do we tell that you know, this is what is going to actually create the polynomial that'll go through those 3 points? Well, we can graph that, and we'll do that in a minute. But I want to point out another way that we could have done this. And so maybe I'll call this coefs1. Okay, find the inverse of A using the backslash. Okay. If we're going to do that, I'm going to say coefs2. And this would look like A backslash Y. And if we go up here, okay, you can see they're the same. Okay. So I want to point out here that the backslash is the more efficient way of solving a system of equations on MATLAB. Okay. So if your goal is efficiency in your code, you wouldn't actually want to solve the system in this manner here. Okay. But what I'd like to do is maybe comment this one out, and just so we don't have two coefficient matrices floating around, I'm just going to call this coefs here. Had the same information in it. Okay. And is what we're told, right, based on, I shouldn't say what we're told, based on how we set this up, if we wanted to graph our polynomial, which I'm going to call P, this right here should be A, the thing that goes in front of x squared. So I'm going to just say coefs 1 times x squared plus coefs 2. So I'm going to pull the second element now. That's B. That's what should go in front of x. And then plus coefs 3, which should be our C. Okay. And again, I showed you all how to use this the other day, but let's use it again. Easy plot. And we'll use the function P. And we're going to also, let's graph this from 0 to 6. Okay. And let's just make sure that we don't get any error messages here. Let's go ahead and run it. Oh, and we did, and I already know what it is. I'm going to fix it real quick. So easy plot is plugging in a matrix here for x, and I should say a vector there for x. So to fix that, we just want to put the little dot there. Okay. Let's go ahead and hit run. Okay, so there it is. Now the question is, does it go through the points that we cared about? So we're going to plot those points. I'm going to say hold on, plot, and those points were pretty simple. Let's grab the x values first. The x values were 1, 3, 5. So 1, 3, 5. Okay. And then the y values were 3, 10, 5. Oh, no, sorry. Yeah, 3, 10, 5. Okay. 3, 10, 5. And when we plot these, we don't want to connect them with a line. These are just points. Let's use the asterisks. Okay, and so we can see our polynomial. It does indeed go through those 3 points. Okay. And that is all of chapter 8.